Hello, today we will be entering into a lecture regarding VA characteristics of MOSFET. So now here, it's very important to know the VA characteristics of MOSFET in order to understand how a MOSFET or a transistor will be behaving depending upon the input voltage which has been given, and how the electrons or the charge carriers are moving from source to drain through the channel which has been formed once the gate voltage is much greater than the threshold voltage. So now this is how the diagram of a transistor looks like. It's a NMOS transistor here. This is a N plus 2 N plus regions which acts as a source terminal and also the drain terminals of the N transistor, and also here the gate terminal. Gate terminal is a main input source, and this is a substrate upon which this implantation or diffusion of this impurities have been done into this particular silicon substrate. So it's a P type of substrate. So now here, once the gate voltage, that is the voltage between the gate and the source, is been applied, then if that particular voltage is greater than the threshold voltage, what is the threshold voltage? Threshold voltage is a voltage where the inversion of the region or the channel takes place. So here the inversion of the region which is below the substrate below the silicon SiO2 takes place. So that is the threshold voltage. So once the gate, the voltage applied between the source and the gate is greater than the threshold voltage, then what happens? Then a channel has been formed. That's what we call it as a transistor has been turned on. Nowadays the minimum voltage threshold voltage is around depending upon the technologies. As per the least technology which I have come across is 0.4 volts is a threshold voltage of a particular transistor. Depending upon the it varies depending upon the technology which you are used in order to design that particular transistor. So now here this particular transistor will be working in three different phases. Three different phases is nothing else but where the transistor always operates or works in three different phases. The first one is called as a cutoff region. That is nothing else but in the cutoff region there will be no channel between the source and drain. The channel will not be existing between the source and drain, so that's why the current wave will not be flowing between these two terminals. So that is why we call it as current is equal to the drain current. The current across this particular drain terminal will be equal to 0. That is a ID equal to 0. That is a cutoff region. Then coming to the next one. The next kind of region is called as a linear region. As we go on increasing this particular voltage between the source and gate, then definitely what happens? The electrons start will get excited and they move from source to drain. There will be a movement of electrons between this source to drain, that is through the channel. So that's why a current has been also increased. So what do we understand from this one? As you go on increasing the voltage across over here, then the current also increases linearly with respect to what is the voltage you have applied over here. So now this is the region where this particular characteristics tells about as a VD drain voltage increases, then at the same time the current also increases. Current across the drain also increases. So now you can see all these characteristics almost is all these three voltages which are drawn between the gate and source are shown over here. All are almost linear in this particular region. It is linear. It means what? Because they are linear, after this region only the bending of the curve takes place. Over here. So since this region has got all these curves linearly linearly proportional between, there is a relationship linearly proportional between the VD and ID, we can call this region as a linear region. Now coming to the next kind of region, that is called as a saturation region. What happens in the saturation region? Once a particular transistor comes across the VDS, that is a drain source voltage, which is equal to which is equal to VGS minus VT. This is the point where that VD equal to VGS minus VT. At this point, once it reaches to this particular point, what happens is that here even if you go on increasing this voltage, if you increase this voltage, there will not be any kind of increase in the current across the drain. It means what? The current across the drain is being saturated. The current remains almost same. Saturated means actually in our textbook we studied as a current is going to be constant, but in fact it's not saturate exactly constant, but there will be some small amount of increase. If it is let me say at one point this is Vd equal to 1.1. For the second point, it might be at around Vd equal to 1.15. So there will be a small increase in the exponential increase in the Vd, but almost it will be equal to a constant. So that's why we call this region, entire this region where Vd is equal to Vgs minus Vt, that is called as a saturated region. Now, coming to this one, why does this bending of this curve takes place? The bending of curve takes place because of the increase in the resistance. Because whenever this saturation region, whenever Vd equal to Vgs minus Vt, at that point what happens here, the current is going to be constant. Because of the constant current, as per the laws which you have studied as a Kirchhoff laws, definitely what happens, the resistance increases. So resistance will be increasing. Because of this increase in the resistance, that's a resistance RON, because of that one, because of that resistance, this bending of this curves takes place. So this is regarding the three different regions of a MOSFET. MOSFET, that's in fact it is an N MOSFET. Next we'll try to see how to derive these equations, or how to derive a relationship between the VI characteristics, or between the V and I of a particular transistor. That's the current, drain current, and also the this particular voltages. So for that one, first we need to understand what is meant by capacitor, MOS capacitor. Why we are coming across capacitor over here? See, what is capacitor? Capacitor is nothing else but it's a parallel connection of two conducting plates. So in the same way here also, this region, this is called as a channel length, the channel region, which is an active conducting part here, and also this gate is also an active conducting part. Between these two, this both will act as an conducting plates or the conducting regions. Between the two, there is a SiO2, that's a dielectric. In this, it is similar to capacitor. Between the two parallel plates, conducting plates, there will be a dielectric between them. That's dielectric is nothing else but it's an it's almost equal to our SiO2 or insulator. So similar, we can call it as a MOS capacitor. So we are supposed to, we will consider as a MOS capacitor, and then we'll start our derivation with the from the point of MOS capacitor. So first we have studied about current, what is meant by current, and how the current is being flown. What is current? Current is nothing else but it's a flow of charge with respect to time. So I equal to Q over T. So we are supposed to understand this equation, and we'll start again deriving what is capacitor. The charge to the capacitor equal to Q equal to CV. Then again, what is a Q equal to CV? Then we know what is C. C is a capacitance stored in the capacitance across the capacitor. That is equal to it is equal to A times of E naught ER by T. That's by D, which is not, what is D? D is distance between these two plates, that we call it as an width of this particular channel. And so this is how we will be deriving this one, and once we derive, we'll get all the equations. Thank you.